Presenter number 1, Brendan Disroot, who will increase our knowledge in the aspect of what are computational methods and how they are implemented in Gaussian software.
My name is Brendan Disroot, and I'm going to give a brief overview of electronic structure methods in computational chemistry. First off, what do these do? The most simplest way to say what they do is they help us calculate the energy of the system and the parts of the system and the energy in those. And those will right. And those will help us get some useful outputs, like we can find the geometry, and the absorbance and band gaps of semiconductors and such. As you know from using the Gaussian software, there's a plethora of computational methods, and if you've ever wondered, the abbreviation's got the full name on this side. But I'm going to be focusing on kind of the top of that list there. And let's jump into it. The molecular mechanics method really it's important if you run this that you specify the bonds between the atoms, because it will treat the bonds as if there's like two masses with a spring in between. And you can really see that in the energy equation there. It's like, your 100 level physics spring equations for a lot of those terms. And, atoms that aren't bonded together, like two different molecules, it'll just run calculations with like Coulomb forces and van der Waals. That's, the easiest to compute. But moving on to what we've been learning a lot in class is the HartreeFock methods. The regular HartreeFock methods will simplify the many-body Schrodinger equation by a couple ways. Firstly is by having electrons get acted on by a mean field instead of, potentially hundreds of other electrons, making it, a one interaction instead of hundreds of interactions to compute. And then you can estimate the many-bodied wave function for all of the different parts as just a single Slater determinant. Based off the HartreeFock method, there's a couple others, like the semi-empirical method, which is like HartreeFock, but it excludes some of the computation parts and will just substitute in experimental data for those. And then the Muller-Placet, which will run a regular HartreeFock calculation and then add in a polynomial at the end with, like when you're choosing the method, there won't be an n, there will be a number, and that's how many terms in the polynomial there will be. Finally, there's going to be EFT, which I'm going to mostly skip over here because we'll be learning about that in the next section of our class. So if you're a guest, feel free to stop by next presentation to get all you want and more. So, in conclusion, there's basically the best in computational cost are going to rank worst in precision. And you really just want to find a balance for how precise you need your results and how long you want them to be running. If there's something that was just more precise for less effort, everyone would use it and there'd be no other methods. So, yeah, that's about it.